convolution. If that word just makes you want to run for the hills, stick around, because today we're going to see that it's not some scary abstract equation. Nope, it's actually a super powerful, really intuitive idea that's kind of like a fancy kind of multiplication. Okay, let's get into it.
All right, to get our heads around this, let's imagine a really simple problem. Let's say you're running a hospital. You've got your treatment plan all figured out, and you know exactly how many new patients are walking through the door each day. The big question is, how much medicine do you actually need?
Now, if your plan is super simple, like every patient gets 3 units of medicine on their very first day and that's it, the math is a piece of cake, right? You just multiply your plan by how many patients show up. But what if the plan is more complex? Say it's a 3-day treatment where the dose tapers off. Suddenly things get messy. The patients from Monday are still getting treated on Tuesday, overlapping with the new Tuesday patients, and it just gets tricky to track.
So, how in the world do we organize this chaos? Well, the solution is actually beautifully simple, and it's visual. We're just going to line everybody up and walk them through our virtual hospital one day at a time.
Okay, our first step is definitely the weirdest one, so bear with me. We are going to flip the patient list. So Monday's patients who arrive first actually go to the end of the line. This puts them in position to be the very first ones to enter our system. I know it sounds backwards, but this little flip is the secret sauce. You'll see why in a second.
Next, let's picture our treatment plan, that dose of 3, then 2, then 1, as a series of 3 rooms. When you arrive, you go into room 1 and get 3 units. The next day, you move to room 2 for your 2 units, and so on. This plan, these rooms, that's what engineers would call the kernel.
All right, it's Monday. The line of patients moves forward 1 spot. That single patient who arrived today enters the first room and gets their 3-unit dose. So, the total medicine used for the day? Super simple, 3 units.
Now it's Tuesday, and this is where the action starts. Everybody slides forward. The patient from Monday moves into the 2-unit room. At the same time, the 2 new patients for Tuesday enter the 3-unit room. All we have to do is multiply the number of patients in each room by that room's dose, and then add it all up. For today, that gives us a total of 8 units.
Let's do just one more day so you can really see the pattern. It's Wednesday. The line slides again. Our Monday patient gets their final 1-unit dose. The 2 Tuesday patients get their 2-unit dose, and 3 brand new patients show up for their first 3-unit dose. We multiply and add it all up, and we find we need 14 units for Wednesday.
So if we keep this process going for the whole week, and we have to remember that patients who started on, say, Friday will still need treatment over the weekend, we get this complete schedule of exactly how much medicine we're using each day. And guess what? This entire process we just walked through, the flip, the slide, the multiply and add, that is convolution. That's all it is. It's just a systematic way to figure out the combined, overlapping effect of 2 different things interacting with each other.
So, let's just lay it out cleanly. You can convolve any 2 signals in these 4 simple steps. 1, you flip one of them. 2, you slide it along the other one step by step. 3, at each step, you multiply the parts that are overlapping. And 4, you add up those products to get your final answer for that one position. Flip, slide, multiply, sum. That's it.
Now, the more textbook definition would say something like this. Convolution is a mathematical operation that expresses how the shape of one function is modified by another. Which is exactly what we saw, right? It told us how our stream of incoming patients was shaped or modified by our specific treatment plan.
Okay, now this is the part where a lot of people get scared off. They see the formal math equation and think it's some totally different, impossible thing. But I want you to look at it and just know you already get what this is doing. It's just our hospital story in a different language.
And there it is, the famous convolution integral. This is just the formal, mathy way of writing down the flip, slide, multiply, and sum process we just did. It looks intense, I know, but let's quickly map it right back to our hospital analogy.
This is where it all clicks. Our treatment plan, the rooms, that's the function f of t, what we call the kernel. The flipped and sliding patients, that's what g of t minus t represents. That big S-shaped symbol, the integral sign, that's just the fancy way of saying sum everything up. And t, that's just whatever specific day we're calculating for. It's a perfect 1-to-1 match. See, you totally got this.
Okay, fine. So it's a cool math trick, but where does this thing actually show up in the real world? Why is convolution considered one of the most important ideas in all of engineering and science?
Well, the short answer is pretty much everywhere.
Convolution is absolutely fundamental to signal processing. Think audio effects like reverb or financial moving averages. It's the engine behind image processing, doing everything from blurring to sharpening to finding edges. And yeah, it's the convolutional in convolutional neural networks, which powers so much of the AI we use every day.
Let's use a really easy example: blurring a photo. Blurring an image is literally just a convolution. You take your image and you convolve it with a small blur kernel. That kernel is basically a little program that tells every single pixel, hey, I want you to average your value with all your neighbors. The result? The entire image gets smoothed out, or blurred.
Now, doing all that flipping, sliding, and multiplying, especially for huge signals, like a high-resolution photo with millions of pixels, well, it can be incredibly slow. It takes a ton of computer power. But thankfully, there's an absolutely magical shortcut. And this shortcut has a name. It's called the convolution theorem. Its magic comes from another legendary mathematical tool that you've probably heard of, the Fourier transform.
And this right here shows you why it's so powerful. The theorem says that doing a convolution in the time domain, which is our normal everyday world, is the exact same thing as doing a simple element-by-element multiplication in the frequency domain. So all that hard work of flipping and sliding and adding, it just becomes easy multiplication.
I mean, this is a total game changer. You can take your two signals, use a fast Fourier transform to pop them over into the frequency domain, multiply them together, which is super fast, and then use an inverse transform to bring the result back. It turns a computationally brutal problem into a ridiculously fast one. This is why engineers and scientists are so obsessed with the Fourier transform.
So let's end with this thought. We just saw that blurring an image is a convolution, which becomes simple multiplication in the frequency domain. So what do you think unblurring is? It's just division. It kind of makes you wonder, right? If a complex problem like a blurry photo can be fixed with simple division, what other blurred problems in our world are just waiting for us to find the right way to look at them to make them suddenly clear?